So let's try this. Explain what is meant by the statement that two bodies are in thermal equilibrium. So remember, thermal equilibrium, same temperature. So conditions when the bodies are at the same temperature. Okay. B. Suggest suitable types of thermometer, one in each case, to measure the temperature of the flame of a Bunsen burner. So you know the flame of the Bunsen burner, they will like keep changing very fast one, you know. So we need a fast response thermometer. So that will be thermocouple. Thermocouple, huh? Okay. Thermocouple has fast response. If you are not sure, you just try thermocouple. Thermocouple at most of the time is the correct one. Okay. Now part 2. The change in temperature of a small crystal when it is exposed to a pulse of ultrasound energy. Okay, so imagine this is a very small amount of energy. A pulse of ultrasound energy is just a little bit of energy only, you know. So we need to use the thermometer that has a small thermal capacity. So it is thermocouple again. Thermocouple. A little bit of energy is enough to make the change in the voltage. Okay, so thermocouple can do that. Now we look at C. Some water is heated so that its temperature changes from 26.5 degrees Celsius to a final temperature of 38.0 degrees Celsius. Okay. State to an appropriate number of decimal places. Okay. How many decimal places in this case actually? So, you know, the decimal place shown here is one decimal place. You can see 26.5 and 38.0. Okay, so you have to give one decimal place okay, for this situation. So find the change in temperature in Kelvin. Okay, so maybe you feel like, okay, should I change to Kelvin or not? So if you change to Kelvin, it will be like this. 38.0 plus 273.15 minus 26.5 plus 273.15. If you are doing mathematics, these two will just cut away, you know. So at the end, it is just 38.0 minus 26.5, so which is 11.5 Kelvin. So 11.5. The final temperature in Kelvin. Okay, so we have 38.0 plus 273.15. Okay, so then you get 311.15 Kelvin. But since the question gives you one decimal, so you can round off to one decimal also. 311.2 Kelvin. So we follow the questions. Yeah, this is the basic one. Now let's see something else. Okay. 3A. Two bodies are in thermal equilibrium. State what is meant by thermal equilibrium again. So you can just read the answer from left hand side. A condition when the bodies are at the same temperature. Okay, so this one settle. So you can refer here. Okay, we look at B. The temperature of a body is found to increase from 15.9 to 57.2. Determine in Kelvin and to an appropriate number of decimal places the rise in temperature. Okay, so same, right? So 57.2 plus 273.15 minus 15.9 plus 273.15. So we get 41.3 Kelvin. Final temperature 57.2 plus 273.15. So we get 330.35. So since the question give one decimal, so here we round off to one decimal. Okay, so the starting looks the same, but part C is something different already. An ideal gas at a constant pressure of 1.2 times 10 to the power of 5 Pascal is heated from a temperature of 290 Kelvin to a final temperature of 350 Kelvin. Okay, so the temperature increase. The change in volume of the gas is 950 cm3. So the gas expand also. Okay, expand. There's a change in volume. The total change in kinetic energy measured in joules of the gas molecule is given by the expressions of that. Okay, so determine the thermal energy required to produce the change in temperature from 290 Kelvin to 350 Kelvin. Okay, so thermal energy required. How are we going to understand this? We have to take it like this. The thermal energy is used to do two things. The first thing is to expand the gas, where we have work done, equal to P delta V. This is AS physics. The second thing is the thermal energy is used to increase the kinetic energy. Okay, so the two bracket that I put over there is where the thermal energy is used. It is used to do work done to expand the gas, and it is used to increase the kinetic energy. So we put it like this. Thermal energy required is equal to work done to expand the gas plus kinetic energy. Okay, so P delta V plus 3 over 2 times 1.9 delta T. So these are given. I mean the P delta V, you have to memorize it. Okay, so P, the pressure is given 1.2 times 10 power 5. The change in volume is given 950 cm3. So 950 cm3 change to SI unit and 10 negative 6. 3 over 2 times 1.9. Change in temperature 350 minus 290. Okay, 350 minus 290. Okay, then we get 114 joule for the first one. For the second one, we get 171 joule. Okay, so add up and we get 285 joule. So you have to know something like that. Thermal energy is required to do the work to expand and to increase the kinetic energy. Okay. Okay. The EMF generated in a thermocouple thermometer may be used for the measurements of temperature. And figure 7.1 shows the variations with temperature T of the EMF E. Part A, by reference to figure 7.1, state two disadvantages of using this thermocouple when the EMF is about 1.0 milliwatt. So the problem is at 1.0 milliwatt, you see two possible temperature. So that is the problem. So the first temperature is about 400. The second temperature is about 600 something. Okay, so that is the disadvantage based on the graph. Two possible temperatures. Okay. The other thing is the graph is not straight line. That is also a disadvantage. So the variations is non-linear. Non-linear. Okay. Part B, an alternative to the thermocouple thermometer is the resistant thermometer. Resistant thermometer is the thermistor. State two advantages that a thermocouple thermometer has over a resistant thermometer. So thermocouple is physically small. Physically small. Then you can also say no power required. No power required. So of course you can say something else like readings can be taken at a point. So you can say that also. Or maybe you can say can be used to measure temperature difference. So you can say short response time as well. Okay, so let's move on. Here, right hand side. Okay, let's do a thermistor. A thermistor that use resistance versus temperature. So you see the word here. The electrical resistance of a thermistor is to be used to measure temperature in the range 12 degrees Celsius to 24 degrees Celsius. Figure 3.1 shows the variation with temperature measured in degrees Celsius of the resistance of the thermistor. Okay, so they give us a graph. Now, okay, so let's look at the next page. They give us a graph. Now, part A, right, they ask, state and explain the features of figure 3.1, which shows that the thermometer has a sensitivity that varies with temperature. Okay, so if you look at the graph, right? The graph is something like this. Okay, so I just copy the graph straight away. The graph is like that. Okay, R versus T. The graph is like this. And now what they ask here is state and explain the feature of figure 3.1, which shows that the thermometer has a sensitivity that varies with temperature. So what is that? Has a sensitivity. Uh, what is the sensitivity here? Is actually the gradient. The gradient, as you can see, the gradient is big, small, smaller, smaller, and smaller. Okay, so the gradient is decreasing along the graph. So when you want to state, right, so you can just state it in this way. You can just say it like the gradient varies with temperature. Okay, so then you explain gradient of graph is a measure of the sensitivity. So what is gradient? So gradient is actually the change of R over the change of T. Okay, so this is how we answer about the sensitivity part. So we talk about the gradient. Now part B, at one particular temperature, the resistance of the thermistor is 2040 plus minus 20 ohms. Determine this temperature in Kelvin to an appropriate number of decimal places. Okay, so what we need to do is like this. You look at the graph, right? You find out 2040. Okay, 2040 ohms. 2040 ohms. Then you bring it here. Then you bring it down. Then you will realize it is 15 degrees Celsius. Okay, then there is a plus minus 20 ohm. You will realize if you plus 20 ohm, then they will go up by one box. If you minus 20 ohm, they will go down by one box. Okay, so it's go up by one box and go down by one box if you do plus minus 20. So in that situation, when you bring it here to the temperature, right? So the effect is the same. They will make the temperature go to the right by one box and go to the left by one box as well. So because of that, what we can say is, if you see the graph of on the horizontal axis, one box to the left is just minus 0.2 degrees Celsius. This one is plus 0.2 degrees Celsius if you go to the right by one box. Okay, so this one box is plus 20 ohm. This one go down one box is minus 20 ohm. So we have to see something like this from the graph. And now to answer the question, right? So we put it like this. First, you said when R is 2040, the temperature is 15.0 degree Celsius. So when R is 2040 plus minus 20 ohm, the T is 15.0 plus minus 0.2 degrees Celsius. Then we change it to Kelvin. Change it to Kelvin. So 15.0 plus 273.15 plus minus 0.2 Kelvin. So if the temperature increased by 0.2, the Kelvin also increased by 0.21. Okay, so it's in the same amount. So 288 point. Okay, how many decimal? Again, they said to an appropriate number of decimal places. So as you can see, our graph has one decimal place. Is 15.0 plus minus 0.2. Our graph can read up to one decimal place. So our answer have to initially is like two decimal place, two decimal place for the 288.15. But for the change in Kelvin, is plus minus 0.2, which is one decimal. So we have to match to one decimal. So that is the answer, plus minus 0.2. Okay, so